So yesterday we have discussed till linear transformation. So basically, more or less, most of the part of it fine. So do you have any doubt till that point? At least the nullity of a matrix, the non-space of a matrix, rank. At least those part are clear. Or do you have any doubt? You can ask me. Still doubt. But in that, okay. So let's start with the discussion for the next part. Is my screen visible?
Yes, sir, it's
Yes,
visible.
sir.
Yes.
Yeah. So I mean, can some of any one of you can tell me what is the linear transformation? We have discussed yesterday, but still, what is the linear transformation? You know, if the session is little bit interactive, I think that will be good. So you can participate. I mean, it's nothing about right or wrong. Whatever you have understood about that question, you can just tell me. So if I tell the word linear transformation, what do you think about that? What is a linear transformation? I'm audible, right? Am I audible?
Yes, sir, you are audible.
So can some of you just we are just recapping the what we have done yesterday. Can someone just tell me what a linear transformation is? What do you understand by that? Linear transformation. Okay. Answer anything.
Sir, two vectors are said to be linear transformation if they satisfy two property f of v1 plus v2 is equal to f of v1 plus f of v2.
Right.
F of scalar multiple c v1 is equal to c into f v.
Right. And so first of all, linear transformation is a mapping, right, from one vector space to another vector space, which
Yes.
satisfy these two properties. Right. So yeah. So if I take this as my map, map T, which is a map from V to W, where V and W both are vector spaces. Right. So vector space means it has some addition. So vector space means it has some addition and it has scalar multiplication property. So if I take two vector from this side, V, two inputs, and if I add those, so I get a new vector V1 plus V2, and the image of these two vector TV1 and TV2 I have on this W. There is addition in W. If I add that addition, these two images should be same. That is one thing we are demanding. And the second one is if I take CV, it should be T of C, C of T. These two property we need for a vector space. So yesterday I have drawn this diagram if you remember. So suppose this is V, this is W. So I am taking two vector. Here is V1, here is V2, and it has an image here. This is TV1. It has an image here. This is TV2. There
So
is an
one
addition in this side.
this is
Yeah.
What is going on?
Yeah. What is going on? So I am explaining what a linear transformation is.
Okay, okay, okay. Continue.
Okay. So there is a addition on this both the sides. If I do the addition in terms of v, I will get v1 plus v2. It has the image here, that is t v1 plus v2, the image of that. And there is the addition in this side also, inside of w, that is t v1 plus t v2. And I am expecting the image should be same. That is the trivial thing we need. So this is the first one. Similarly, for the scalar multiplication, we need the same thing. P of CV is same as C of TV. So if a mapping satisfy these two property, that we call this a linear transformation. So this is a linear transformation. Right? Till this portion we have discussed yesterday. Now I have given some example also. So let me write some example here. R2 to R3, suppose I am taking, so R2 means vectors will look like x comma y. Suppose I am defining it at x minus y, x, and x plus y, 3 coordinates. Is this a
Yes,
linear
sir.
transformation? Why?
Yes, sir.
Yes.
Why this is a linear transformation?
Sir, because it satisfies two
Yeah.
properties you write about.
It will satisfy these two property. You can check it. Now, if I write this like this, x square.
It's not a linear transformation
Why?
because the power is 2, sir. It's not linear.
So basically, all the coordinates in this side,
Exponent should
whatever
be
it
1.
is, it should be linear combination of x, y, z, whatever the vectors are. So the general form, if I want to write from Rm to Rn, as I have written yesterday, also how it will look like. So Rm means there are m coordinates, x1 to xn. It should be like a combination a I1 and xi, I1 to n. All such condition, all such summation should be there. AI2 xi, this will be the second coordinate, and so on till AIN xi, I is from 1 to n. So this type of, so combination of all these xi's should be there. Maybe some coefficients are 0, maybe some AI1 or AI2, some of them may be 0, but that doesn't matter. Basically, there cannot be some constant, there cannot be some power of the variables. That two things you need to remember. So even if in this transformation, suppose I am writing x plus 2, x minus y, x plus y, then also it is not a linear transformation, because this will create a problem, this plus 2. So as I have said earlier, for a linear transformation, 0 must go to 0. That is coming from this first property. This first property will say t of 0 must be 0. So 0 should go to 0. That is the trivial thing we need to know. So if that does not happen, so if there is some constant, then you can check that t of 0 is not going to 0. There is some 2 comma 0 comma 0. So that is not 0 or 3 with the usual addition. So these are the things we need to know. Anyone has any doubt till this portion, or should I move ahead? There are two little things which are remaining in this chapter, in this week. Anyone has any doubt till this point?
No, sir.
No.
Okay, great. Great. So what I can do is, suppose let me write it like this, R2 to R3. The transformation which I have taken earlier, let me write that x minus y, x, x plus y. Okay. I can write it like this. Now, if I want to write it as the summation I have written, so it is 1 into x plus minus 1 into y, 1 into x plus 0 into y, and this is 1 into x plus 1 into y. This is what I got, right?
Yeah.
So Can I write it like this? This is the matrix, some matrix A, and this is the vector x, y, which is coming from R2. So I can write, so you can check, this is first one is x minus y, that is what it is. Second one is x, and third one is x plus 1, right? I have written the same thing, but in a different representation, right? So what I have done is, I have taken a vector from this side, I have written it like this, A, B, right? So any linear transformation I can do this, for any linear transformation. There is a matrix like this A, for which if I take the input and take the multiplication of that vector with that matrix, I will get the output. So that's how the linear transformation is defined. And here it is the, I mean, there is a relation, you can see clearly, relation with the matrix, right? So each linear transformation has a relation with some matrix, right? Is it clear?
Yes, sir.
Is this part clear? So each linear
Yes, sir.
transformation I can write it as a matrix like this, TV as A into B. So suppose, let me check if it is clear to you or not. R3 to R3, and observe that it is from R2 to R3, and what is the order of the matrix? It is 3 cross 2, right?
Yes, sir.
So this is 3 and this is 2. So it is 3 cross 2. So there is some relation with the dimension of the vector spaces, right? So suppose I am taking R3 to R3, and I have written, let's say this. This is again a linear transformation because everything is linear and has a linear combination of the variable. So what is the, if I want to write it as T, B, A, B, what this A is?
1 0 minus 1.
1 minus 3.
1 0 minus 1.
Right. So first
0
one is
1 minus
0
1.
minus 1.
Yeah.
0,
0, 1 minus 1. 1, 1, 1.
Correct. So this is what I am getting, right? If you do this product, I will get back this. Okay. So is it clear to everyone
Yes, sir.
in this point? Okay. Now, so there is a relation of linear transformation with the matrix. This is what I need to point out here. In the next week, we will see it in details. So there is something called matrix representation, and there this, this you will come to know in details. So this is one thing we needed to discuss. And next thing was, when we have read function, so there are some
Sir.
types of function. Yeah.
Sir, there like the matrix which you have written 1 0 minus 1. So it has to be like 1 null, like because x has a positive coefficient.
So basically, I am writing the coefficient. So this is a combination of x, y, z, right? So what is the combination? 1 into x, 0 into y, and minus 1 into z. This is what I have written. This coefficient.
1, yeah. But for the last element should be 1 only, no? Minus 1.
No, this is minus 1, no, minus z.
Okay. I got confused with this.
Yes, so here, if I want to write this one, this is 0 into x, 1 into y, plus minus 1 into z, right? So 0, 1, minus 1.
Okay.
For this one, 1 into x, 1 into y, 1 into z. So all are 1. So 1.
Yeah, I took it as like one element from the x and then from the next element x plus y plus.
So you have to write the coefficient. So even suppose, let me ask you, as you are asking this, 3x plus 5y, 4x minus 3y plus 2z, and z. Suppose I want to write this. Can you tell me what the matrix will be?
It will be 3
3, 5,
0 5.
Not 0. So y is 5.
Yeah, 5 0.
5, 0.
Next one.
And 4 minus 3 and 2.
Right. Next
Then
one.
0 0 1.
0, 0, 2,
Yes.
0, 0, 1.
Right. Got it? How we are writing this? So we
Yes,
just
sir.
taking the linear combination. Whatever the linear combination is there, That is what we are taking, right? Okay. So this is what one thing we
Sir,
made. Yeah.
in this you have discussed the example of XYZ, but if it is given in three basis forms like 100 and then 110 like this, and they are requiring us to find XYZ, then how to go about it?
Yeah. I will come to that. Yeah, that is the thing which remains. So I will come to that discussion. Okay. Yeah. So basically, the next thing what I wanted to discuss. So suppose I know the set T is from R2 to R. I know where this 10 goes. Suppose it is go to 2, 3, and I know what 0, 1 goes. I know it is going to suppose say 4 and minus 5. Suppose I know these two images. So if I give the input as 1, 0, I am getting 2, 3. If I give the input as 0, 1, I am getting 4, minus 5. So basically, I have taken a basis, standard order basis of R2, and I know where the basis goes. Right? Can we find out the linear transformation from this? That is the question. The question is, can we find out T explicitly? So this is the question. Explicit means Txy equal to something. That is what we have to find. Right?
Yes.
So what? Yeah. So what we are doing? So any element of R2 is basically of the form x, y. That we need to find, and any element can be expressed as a linear combination of the basis element. Right? That we know. So I can write it as x into 1, 0 and y into 0, 1. Right? This is what we can do. Right? Now, if I take the t of xy, t is a linear transformation, right? That we know. T is a linear transformation. So what is this? I can take t on both sides. So this. Now, these two are vectors. So I can separate this out. T v1 plus v2. This is v1, this is my v2. So x 1, 0 plus t y 0, 1. Right? Now what I can do? This is a scalar, x and y. These are real number. So I can take this out. TCV equal to CTV. That property. So T 0, 1. Next, T of 1, 0 I know. It is 2, 3. T of 0, 1 also I know. It is 4, minus 5. So what I get here? This is 2x, this is 3x, plus this is 4y, this is minus 5y. So if I add this, what I am getting? 2x plus 4y, 3x minus.
Sir, it is plus 5y only, no, sir?
Huh? Minus 5y, no? 4 minus 5.
4 minus. Oh, okay, sir. Okay, sorry, sir.
Okay.
Sir,
So
the
TXY,
two vectors
what?
we are, excuse me, sir.
Yeah.
The two vectors we are taking in codomain 2, 3, 4, minus 5. The two vectors need to be independent, right, sir?
No, not necessarily. Not necessarily. There can be anything. So this is saying that if I know the image of the basis element of the domain, then I know the linear transformation. That is what it is saying. I don't bother about the image. It can be anything. Let me give you an example. So this example you have understood, everybody?
Yes, sir. Yes, sir.
Anyone has any doubt in this example itself? Anyone?
No, sir.
No.
Okay. So suppose you are asking whether the image of that portion need to be independent or not. So suppose I am taking it 0, 0. I can take this as 4, 0. I can take like this. And so the images are not linearly independent, as you can see. There is 0, 0. Even I could take both as 0, 0. So what will be the linear transformation now? T of xy is x t of 1, 0, y t of 0 comma 1. What is this? X t of 1 comma 0 is 0 comma 0, and this is 4 comma 0. So eventually what I am getting is 4y comma 0. This is the linear transformation. Got it?
Yes, sir.
Yeah.
Thank you, sir.
Now can someone tell me, if I take both the images 0 comma 0, what will be my linear transformation?
0 comma 0.
0 comma 0.
0 comma. So it is a 0 transformation. Yeah? Every element is going to 0. Now the nice thing is, here I have taken the standard order basis. It may not be standard, right? Let me take another example. Suppose it may not be a standard, so I am taking say 1 comma 0 and 1 comma 1. This is also a basis of R2, right? Correct? This is also
Yes.
a basis of R2. Right?
Yes.
Is it
Yeah.
clear to everyone? Why this is a basis of R2?
They
Because
are
there
independent and two
The minimum
Two
spanning.
Correct. It is really an independent set of two vectors, so it is a basis. And even if someone can check its spans, also it is a span. So basically, what I need again, I need to write x comma y in terms of these two. So I need to find some a and some b in terms of x comma y, right? I need these scalars.
Yes.
Correct? So
Yes, sir.
what I need is a comma 0 and this is b comma b. So this is a plus b and this is b. Right? So a plus b should be x and b should be y. So as b is y, what should be a? It is x minus
X
y.
minus Y.
So basically I can write x comma y as x minus y into y 1 comma 0 plus y into 1 comma 1. Correct?
Yes, sir.
Any doubt till this point?
No, sir.
So now suppose
Sir.
I know the image. Yeah.
Sir, do we always have to take like here 1 comma 0 and 1 comma 1 as like it has to be basis in R2,
It has to be basis in R2. It can be any basis.
but
That
it
is
has
what
to
I
be
am.
but that has to be a basis.
That has to be basis.
Okay, sir.
Right. Then only we can have the full explicit transformation. Otherwise we cannot have. Then only we can get what the linear transformation is. Okay.
Okay, sir.
So
So,
suppose
sir,
this.
if we change the basis, means transformation will change.
Right, as you can see. So if I take the same images, so as the first one, let's see whether it changes or not. So for first one, the first element was going to 2 comma 3 and second element was going to 4 comma minus 5. Suppose I am taking the same thing. 2 comma 3, 4 comma minus 5. Right? The same thing I have taken, but here the basis elements are different. So this is the expression I got. So t of xy, what is this? This is x minus y into t of 1 comma 0 and y t of 1 comma 1. Now let's check what the element I am getting. This is 2 comma 3 and this is 4 comma minus 5, right? So what I am getting? 2x minus 2y, 3x minus 3y, and here is 4y minus 5y, correct? So if I add it, this is 4y, 3x minus 3y minus 5y. So what I am getting? 2x plus 2y, 3x minus 8y. This is the linear transformation I am getting, which is different from the earlier one, right? Earlier one was like this. So now it is different, as you can see. Because the representation is different. The representation with respect to this basis element, this combination is different. So obviously the map will change. Got it?
Sir, so the process should be like we have to first compute what is the coefficient in terms of x and y.
Right, right.
And
right.
then
what is the linear combination? That you have to find first.
Yeah, then put the transformation, means function, and then put the values.
Exactly. Okay. Right. Clear? Is this question clear? Anyone has any doubt at this point? Anyone has any doubt?
I don't understand the last step.
Which
Transformation.
step?
Transformation.
Which step?
Sorry?
Which step you don't understand?
Transformation.
The definition of transformation, is it?
Yeah,
Have you joined just now?
yes, sir.
No, right? You have joined from the beginning, right?
But I still don't understand last step.
So when I was asking, you were not saying anything.
Stand. I understand this, but in the example, I don't understand how to do it.
So suppose I know the images of the basis element, right? This is what I have written here.
Mm-hmm.
So you know what a basis is, right? For R2.
Yes, yes, sir.
What is the basis?
So basis after spanning once you like how I tell you, I don't know, but I know basis.
Is this a basis of R2?
Yes, yes,
This one,
yes.
1001.
Huh.
Is this a basis of R2?
Yes, sir.
This one.
No,
Why?
sir. 1001 is basis.
And this one is not a basis.
No, I don't.
If I write like this, then
One here is basis one. Yes, it is also.
why? I mean,
Uh,
what is the difference it is creating?
Side. I'm not able to tell you how, but I understand this maybe.
Suppose I am writing this. Is this a basis?
No, no,
It's not a basis.
no. Wait a second. After spanning, maybe it's basis. It needs to
Maybe
span.
no. I mean, either it's a basis or it's not a basis, right?
Yeah, yeah. It needs to span.
So can you how we will check that this is a basis or not in R2?
After RREF.
So basis means what? It must be linearly independent and it should span the whole R2, right?
Hmm.
Now, if a set inside R2 has two vectors and
Yes,
it is
yes.
linearly independent, then it's a basis, correct? Yeah. So how we can check that this set is linearly independent or not?
Wait a second, sir.
Yeah. So basically, you have to check the determinant. Okay? You write this as column, you check the determinant. If it is determinant non-zero, then it's linearly independent.
Yes.
Correct? So then it has two elements, it is linearly independent, so it is a basis. Now, what I am saying is, I am taking the images of these two elements, the basis elements. So one basis I have taken 10 and 01. This is the standard basis. I have taken the image of this with respect to some linear transformation. Now my question was, can we write T explicitly? That means Txy is something. Can we write that? So how we should do that? So xy is an element of R2, so I can express it as a linear combination of these two elements, right? Because this is the basis, correct? Are you there?
Yes, sir. Yes, sir.
Huh. So I can write xy as a linear combination like this: x into 1, 0 and y into 0, 1, correct?
Mm-hmm.
Huh. Now I am taking t on both sides. Now
Oh,
this can be splitted, right? This is v1, this is v2. So t v1 plus v2 is t v1 plus t v2. That is what I have written.
yes, sir. Now I understand. Yeah.
Now this x is the scalar. Scalar I can take outside.
Outside.
So tcv is same as ctv. That is what I have done here.
Sorry.
Now you know the images of t01 and t10 and t01.
Yes,
I have
yes, sir.
that images,
Yes.
and I can calculate it. I get the
Okay.
explicit definition of it.
Okay. Okay. Thank you.
Got it?
Yeah.
Yeah. So that is what I am doing. So yeah.
So one question here.
Hmm.
So here, the first example,
Right.
we are not using the coefficient A, B. Or directly
This
we
is
are
standard.
saying
So obviously it is x and this is y. I mean, you can write it as this
okay.
and then solve it. Then you are getting basically a equal to x and b equal to y.
Okay, because it is standard basis. That's all.
I mean, you solve it. This is a comma 0. This is 0 comma b. So it is a comma b. So a should be equal to x, b should be equal to y. So for standard, we don't have to bother about this, right?
Okay.
Because standard is basically first coordinate is the first one, second coordinate is the second one, third coordinate is the third one, like that. That's why it is called standard.
Okay,
Right?
sir. Noted.
Yeah.
Thanks.
Yeah. So understood what we are doing here? How from this definition, I mean, if we know the image of the basis element, we know the transformation explicitly. That is the outcome of this discussion, right? Is this clear to everyone? Is
Yes,
this
sir.
clear to everyone? Oh, great. So this
Sir,
is one thing. Yeah.
just one query.
Yes, yes, sir.
Here, this one, whatever vector you have written in front of t, means t of xy. So this xy should be treated as domain, and whatever is the right hand side, it should be treated as codomain, right?
Right. I mean, xy is not the domain. The domain is the whole thing. This portion. This is the domain. Domain is the whole vector space, right?
Okay.
No, not okay. I mean, you have remembered. I mean, in math one, you have learned what is a function, right?
Actually, in functions, that domain and range is given, so that's why I just am
So what
trying
was
to
domain in the
correlate
function?
thing.
Yeah, right. That is what I am doing. What is domain for a function?
It's a set of all values that satisfy the function. And that the values
So
which the
basically, set of
function
all
can take.
inputs, right? Yeah, correct. So here, what are the inputs function can take? All the elements of
All
R,
the real numbers.
right? So this side is my domain. This is my codomain. Right? Same as function because transformation is the function. So yesterday I have started with that discussion. So there is my domain, there is my codomain, and it is the function is from here to here. Right? Now transformation is a special type of function because here my domain and codomain both are vector spaces. That's it, nothing else.
Okay.
Is it clear?
Yes.
Okay. Okay, fine. So this we have understood more or less. Now the next thing which you have read in terms of function, two type of function you have read. One is one-to-one, that is injective, another is on-to function, right? That is surjective. So anyone remember what an one-to-one function is?
A unique image of every
One
like
input
every
gets
yeah.
For
proper
every
one output.
input, there is only one output.
There is exactly one output.
I mean, always one input should give one output. That is the
When
definition.
distinct inputs have distinct outputs.
F of V1 equal to F of V2 only if V1 equal to V2.
What does it mean?
Sir, for any image in the domain,
No, it's not acceptable.
it's the image is it's for any value in domain. Its image is unique. Should be unique.
So more or less you got the idea. So
So
basically,
in simple
what I can say,
words, we can just say that if we consider a domain, then two elements should not point to a single image.
exactly,
That is the
exactly. That is what I
moral.
exactly. Two element cannot give a same output. This is not possible for one-to-one function. Okay. Two input cannot give same output, right? So when I am saying t v1 equal to t v2, that means here there are two v1 and v2. They are giving me same output. This is from v1 I am getting t v1, from v2 I am getting t v2. If these two are equal, then these two cannot be distinct. These two must be equal. That is what the definition was. Clear? Same
Yes, sir.
definition
Yes, sir.
works. Same definition works here. I mean, because transformation is a function, so one-to-one transformation means it is one-to-one function. Correct? If same definition, this one. This is the definition of one-to-one transformation. Okay? Clear?
Clear, sir.
Okay. And what was definition of onto?
Like all the
One
codomain should be
input,
used.
many outputs, sir.
Yes.
No, that is not a function.
For
All
One output and can have
Many
many
out-
inputs.
Oh,
no,
okay.
no, it's
So,
one
For
and
each
it should be
output, there should exist three
for
images.
Exactly.
each element in codomain, there should be at least one pre-image in the
yeah, more
vector
than one. Yeah, that's fine.
No, not more than one. Maybe one also. Why more than?
At least one, sir.
But their
The
exact
At least
means
the
they need
codomain
to
should
unique.
be the range of the function.
Okay.
correct.
Yes.
That is also right. So basically, take any element from the codomain, any element that must have a P image. There should be something here from which where it is coming, for which input I am getting that out. So that was the definition of on, right? So for each W in W, there exists V inside V such that PV equal to, right? We are taking any element from W, this small W. There should be a P image of that. What is the meaning of P image? There should exist some V inside my domain for which the output is W. Clear? At least the definition is clear pictorially,
Yes, sir.
correct?
Yes.
Yeah. So this is the same thing happens for one-to-one transformation. So here I should write transformation. One-to transformation. So this is called injective, and this is called surjectivity. Okay. So same thing works. So now let's check some example. Check with some example. Say t r2 to r2. Suppose gxy is going to x comma 0. Right? First tell me whether this is a linear transformation or not.
Yes, sir. Linear.
Yes, sir.
No, sir, it's not a linear transformation.
It's not a linear transformation. Why?
Sir, for 0, 1 0 also give
So all the
image
conditions are 0.
0. Sir, I got it. It's a linear transformation.
It's a linear transformation, right? Yeah. So you can check the two property will be satisfied, or it's a linear combination of all this. So basically I can write 1 into x plus 0 into y and 0 into x plus 0 into y. This I can write, right? So my matrix will be like this. Right? This is what I am getting. Yeah. Right. So this is a linear transformation. Now first question is it 1 to 1? Is it 1 to 1? So, is there,
No, sir.
does there exist two element which is going to same element?
Yes, sir.
Can you give me an
1,
example?
1, comma 2.
1 comma 2.
1,
Okay.
comma 1, 1, comma 2.
Correct. So if I take 1 comma 1, so whatever, if I fix just x coordinate, I will get the same image, right? Whatever y value I can take. So for image of 1 comma 1 is 1 comma 0. Image of 1 comma 2 is also 1 comma 0, right? So there are two elements which is going to the same image. So this is not 1 to 1. Correct? So for a linear transformation, what we generally do, so I will come to that question later, but still see which elements are going to 0. Can you point out which element are going to 0?
All the elements of y.
All the elements of R2.
All
Y-axis.
Y-axis.
in place of x 0.
It's all the
because-
So if I
y-axis.
take Y-axis, if I take 0 comma y,
Yes, 0 comma y.
then the image is 0 comma 0, right? For any y, right? So all the elements on the y-axis will go to 0, right? Okay. So remember this point. I will come back to this. So this is not 1 to 1. That is at least clear. Is it on to? Is it on to?
Sir.
Yes.
Why?
Sorry,
Yeah.
because one input pointing to outputs, many outputs. No?
Sir, there is no pre-image
Surjectivity
for
was
0, comma
not
1.
like that. Surjectivity was I am taking any element from R2, which is the codomain here. I should take some element from there. I have to check that whether there is an input or not for that element.
Okay.
There is nothing called one many in this onto definition, right?
Okay, sir.
So does every element of R2 has a pre-image?
Yes, sir.
Yes, sir.
Yes.
Okay. Suppose I am giving you 1 comma 2 inside my R2. Does it have a pre-image? So is there exists something comma something such that t of that is 1 comma 2?
No, sir.
Can I
No,
get?
No,
sir.
no, because it's 1, 0.
Then 1 comma 2 does not have a pre-image, right?
Yes.
Yes, sir.
So basically, if I take any element which is not on x-axis, then it does not have a pre-image, right? Because second coordinate is always 0. So if I put something in the second coordinate, that element does not have a pre-image. So every element of R2 does not have a pre-image. Is it clear?
Okay, sir.
So no pre-image.
Yes.
Clear? So it is not on.
Okay.
Any doubt in this question?
No.
Sir, while checking uh, on to like 1 comma 2 and all you have given, right? So it need not necessarily be the range in which the R2 which we are defining, like x comma 0. So the image need not be only 1 comma 0, 2 comma 0 or any x comma 0.
That is the image set, but what is the codomain here? Codomain is R2.
Okay.
What you are saying, that is your range set. Correct. Range set is what? Range of T. All this type of element.
X
Right?
comma 0, yeah.
Right. This is your range. But what is codomain of T?
R2 fully x
Codomain is
comma.
R2. That is given. Right?
Okay.
So these two are not equal. Range and codomain are not same. So another definition of onto was range and codomain should be same. Right?
Okay.
Here it is not.
Okay.
Correct?
Okay, sir.
Understood?
Sure, sir. Sure.
Okay, great. Let me give another example.
Sir, like I'm unable to visualize how all the y-axis is going into 0 to 0.
This is 0 comma y. What is the image of 0 comma y? If I put suppose 0 comma 5, what is the image of 0 comma 5? T of 0 comma 5. Can you tell me what is the image with respect to this function?
It will be 0 comma 0.
That is what I am saying. You take any element here, 0 comma something. That is your y-axis, right? 0 comma something.
So that
This
like
type of element
yeah.
are on y-axis, right?
So whatever y value we take, it's always going to give 0.
Right. Correct.
Yes, sir. But how
So
can we
whatever-
present it visually? I get it here, but can we represent it visually like something graph?
So this is your y-axis, right? 0 comma y.
Yes.
So this is going to 0 comma 0. That is what it is saying.
Okay.
I am not getting what you are asking.
Like I was asking to can we represent it using graph?
So, I mean, you understood what this transformation is, right?
Yeah, I got it.
Okay, so it is from R2 to R2, correct? So here I have a R2, here I have another R2. The map is from here to here, correct?
Yes, sir.
How the map is defined? Take any element from here, anything, x comma y. Everything is falling on this axis. The image is on this axis,
Yes.
x comma 0, right?
Yes.
Whatever element are coming from here, anything, the image is this axis, on this axis. Correct?
Yes,
And
sir.
all the elements on y-axis, this, that is coming to this point, 0, 0. This is the visual
Okay.
element.
Yes, sir. Yes, sir. It's nice. Thank you. I got it clearly.
Okay, fine. Next, let me give you another example. Say, so R3 to R2. X, Y, Z, x plus y, x minus y. Okay, now tell me, is it, let's say here I can put Z also. Is it 1 to 1? This is the first question. Is it 1 to 1? So what does it mean? Are there two elements which are going to the same image? Is this happening in this case?
No, sir.
Sure?
Please repeat, sir. What, sir?
Is it 1 to 1? That is the first question. Are there two elements inside the domain R3? Here the domain is R3. So are there any two elements in R3 which is going to the same image?
Yes, sir.
Yes,
Like
sir.
1, 1, and 2, 0, 1 can lead to 2, 1.
So what you are saying? 1, 1, 1.
Yes, sir.
So it is going to 2, 1.
1.
And what was the other thing?
2, 0, 1.
2, 0, 1. That is also going to
2, 1.
it is 3.
2, 3.
It is not 2, 1.
Okay.
2, 0, minus 1.
Minus 1.
Minus 1. So it is coming to 2, 1. Right? So this is not 1 to 1. Okay.
Sir, how to get this counter example, sir?
Yeah, now this point. So earlier example was easy to find the counter example, but this is not so trivial, right? That is what you are feeling. Here there is a point to checking 1 to 1. So that is what I am going to tell. So this comes, here comes the null space of T. Okay. So this null space topic is actually coming in the next week, but still I am defining it here. So this is all vectors inside my domain which is going to 0. Okay? This is called null space. Okay? All those vectors which are going to 0. So how does it pictorially I can represent? This is my V. This is my W. Now all these vectors which are going to 0. There is something 0 inside W, right? All those vectors. So this is my null space.
Is it similar to kernel?
It is counted, not similar. It is counted. Okay. Null space and counter are the same thing. Okay. So this is the definition of null space. Now, can you tell me if T is 1 to 1? Can we tell something about the null space? Think, what can I tell about the null space?
Nullity should be
Yes,
0.
sir.
Only 0.
So observe that 0 is always going to 0, right? 0 is always going to 0. Now, if there exists some other element which is going to 0, then this is not 1 to 1, correct? T of 0 is always 0, right? If there are some other element, T of V is which is going to 0, then V is inside the null space, then this is not 1 to 1, right?
Yes.
So if T is 1 to 1, that implies this null space must be 0 vector space. Only 0. Singleton set. 0 vector space, right?
So,
Correct? So here I should mention one thing, that this null space is also a subspace of T. It's subspace of T. You can check it. So in the last live session I have checked for matrix. So same kind of checking will go here. T of 0 is going to 0. If there are two elements inside the null space, V1 and V2. Then what about T V1 plus V2? This T V1 plus T V2. And both of them are 0. So 0 plus 0, this is 0. So V1 plus V2 is inside the null space. Correct? And what about the scalar multiplication? If V is inside the null space,
C times 2.
C times
C
0
times V,
equals 0.
T of C times V is C of T times V is C into 0, that is 0. So CV is inside null space of T. Right? So this is a subspace. So if T is 1 to 1, then the null space must be 0 vector space. No other element should be there. Right? Correct? This is understood?
Yes, sir.
Okay. Next, what we know, the converse is also. What does it mean? If null space is 0, then T must be 1 to 1. How we can show that? So I have that null space of T is 0. Only 0 vector is there. Right? Now I want to show what I want to show. T is 1 to 1. This is what I want to show. So T V1 equal to T V2. Let us assume this. What I have to prove? V1 equal to V2,
V1
right?
equal to V.
Yeah. What is given? This is given.
V1 equal to V2.
So we have to show V1 equal to V2 if I want to show T is 1. So if I take both of them on same side, what I get? It's 0, right? And can I write this as T V1 minus V2 is 0? Because T is a linear transformation, right? What does it imply? It implies that this V1 minus V2 vector, this is a vector. It is inside the null space, right?
Yes, sir.
It is inside the null space. Now, what was my null space? What was given? It was only 0.
Only 0.
So V1 minus V2 must be 0.
Yes.
What does it imply? V1 is 0.
T of 0 is equal to 0.
Clear? So, good way to check the null space. This is good way to check the 1 to 1. So, this is the standard one. This is what the powerful. I mean, I told you at the beginning that linear transformation is more powerful than function. So, this is one of the reasons. So, here T is 1 to 1 if and only if the null space of T is 0. The kernel of T is 0. Only the 0 vector. So, there is only one vector which is 0 is going to 0. No other vector will go to 0. Now come back to this question. I will go back there again. So, which are the vectors which are going to 0? How can we check it?
Sir, we can write linear combination of vectors.
So,
System of
basically
linear
the
equations.
image should be 0. So, when the image is 0, 0, so if these two equation will give me 0, right? We have to find the solution of these two equations, correct? Correct?
So no
All those
solution
equations.
goes to.
But
Now we have to construct a matrix and find solution.
correct. So basically we have it boils down to the same thing what we are doing earlier, right? So basically if I want to find the null space of this T, what I need all those x, y, z for which T of x, y, z is 0, 0, 0, 0 in this case, right? Now what is T of x, y, z? That is x plus y is 0 and x minus y plus z is 0. So all those x, y, z which satisfy these two equations, that is inside my null space, correct? So basically it boils down to set of solution of these two equations, this system of linear equation, right? So let's try to find out one null space. So let me write it down. So what I have started with R3 to R2 T of x, y, z.
X plus y.
What I was written, I forgot. X plus y, x minus y plus z, right? X plus y and x minus y plus z. So if I want to find the null space, I have to solve this equation, right? So what actually I am doing? So I am writing the coefficient matrix. And observe that what is this coefficient matrix? This is nothing but if I write it in the matrix form, as I was writing earlier, it is the same thing, right? This is actually the coefficient matrix, right? This matrix. So what actually we are doing? We are basically finding the null space of this matrix. This is A. So basically we are finding the null space of A, correct?
Yes.
So in my last session, someone asked, why are we calling this null space? Why are not we calling it just set of solution? So it is set of solution, but here is the reason why we called it null space. Got it?
Yes, sir.
So what is the null space? The same thing. Now we are basically finding the null space of A. So the same process will go on. So what is this? R2 minus R1. What was that? 1, 1, 0. So what is that? 0. Tell me. Come on, solve it with me. Yeah.
0 minus 2 1.
Then what is the next step?
minus 2
Divide by
minus 1 by 2.
So this is what 1 minus half, right? What was the next step?
R1 minus R2.
R2.
1 0 half 0 1 minus half. Correct? So this and this, right? So x1, sorry, x here, x, z are there. So x plus half z equal to 0, x minus half z equal to 0. So eventually what I am getting, minus half z, y is half z. So it is minus half z, z, right? Z belongs to R. So this is my null space of T, which is same as null space of the matrix A, right? The same thing. This is the null space of T. Now this is the vector space, right? As you have seen earlier, I have checked. Null space is the vector space. What is the dimension of it?
2.
1.
2.
Why 2? 1. Only one free variable are there.
Okay.
Right? Only one free variable are there. So dimension of this null space, the same thing we are doing as I have done for matrix.
Is nullity.
Yeah, this is called nullity. So this is 1.
1. Okay.
Okay? This is called nullity of T. Nullity of the transformation. Okay? Understood this same type of definition? Now go back to this place where I have written T is 1 to 1, the null space must be 0. What does it mean? What is the nullity of it?
1.
0.
0.
Because null space of nullity is 0, right?
Okay.
So
Yeah.
T is 1 to 1 if and only if nullity is 0. If nullity is non-zero, then T is not 1 to 1. So in this transformation which I have just now calculated, what was nullity? Nullity was 1.
1.
Correct? So this is it 1 to 1 or not 1 to 1?
Not 1 to 1.
Not 1 to 1.
Got it? How we have to find it?
Yes, sir.
So nullity has to be 0.
For if the transformation has to be 1 to 1, the nullity has to be 0. But in this case, what we have calculated, nullity is 1. Because we have found the null space. There are some vectors. I mean, there are infinitely many vectors which are going to 0. Right? If you take minus half, 1, that vector is going to 0. If you take minus 1, 1, 2, that vector is also going to 0. So there are infinitely many such vectors, right? For each z inside R, there will be a vector which is going to 0.
Yeah,
So
it
there
has
are
to
many
be
vectors
empty.
which is going to the same image. Got it?
It has to be empty set.
Huh?
It has to be empty set for 1 1.
Has to be not empty set, only 0. Because empty set it cannot be. 0 will always go to 0. No? 0 will always go to 0.
Zero
You have
vector.
to 0. Right? So if T is 1 to 1, then null space must be 0 vector space. And nullity is 0. Got it?
Excuse me,
Is
sir.
it clear? Yeah.
Sir, in one of the tutorial video, ma'am has told if n is greater than m, if Rn to Rm, then rank should always be equal to n. Mm, from where it comes?
I mean, that is for matrix, yeah, and it's for Rank-nullity also, but that is in next week. And for matrix, I have discussed it yesterday. Which
But
one
sir,
are you asking? Are you asking for
No, it's
transformation
week
or
5 only.
matrix?
sir, it's ma'am was telling 1 to 1 and on to function. They are telling some relation between if there is a mapping between Rn to Rm, then
That's-
n is greater than m.
Hmm.
Then always rank must be equal to n. That's why I am asking. Then function cannot be 1 to 1.
That right. I am coming to that. I will explain. Okay.
Okay, sir.
I will explain. Basically, that is basically Rank-nullity theorem for transformation. That is what we need there. But I will explain it. Nevertheless. So at least till this portion, is it clear what I have said?
Yes.
What I have said is T is a transformation
sir.
from Rn to Rn. Okay. I have some transformation. So basically, I can write TV as AV, as you can see. Now, what I have done here, basically, so what is null space? So let me summarize what I have said till now. So all those V, inside Rm here, so let me call it Rm, such that TV is going to 0, right? And what is the matrix? This matrix is n cross n matrix, right? That we know. This is n cross n matrix. So what does it mean? This means Rm such that AV is 0, correct? So this is same as null space of A, correct? We know how to find null space of A. Now T is 1 to 1 if and only if null space of T, what it should be?
0 vector.
0.
0 vector space. And this is same as the nullity of it. That is 0. Nullity is 0. Correct? And as null space of T and null space of A are same, so same as nullity of the matrix basically. Okay? So this is what we have discussed till now. Correct? So you can check what nullity this means. Now, what about rank? What the rank is basically? Now, let's come to this. Is there anything analogous to the rank of a linear transformation? That is the next thing we find. So, T is V to W mapping. What is image of T? Image of T means TV such that T is belongs to T. All the output, right? All these output, correct? My question is this a subspace? Is this a subspace? So what is the first second? Does 0 belong to here? Does 0 belong to here?
Sir, what is it? INT?
Image. This is
Image
image of
of
image of. So it is written as IM. Okay, image. So yeah, does 0 belong to here?
Yes, sir.
Yes, because T of 0 is 0, so 0 belong
0.
to here, right? Yeah, so 0 belong to image of. I don't have to bother about that. Now, suppose I am taking two elements, W1 and W2. Both of them belong to image of T. What does it mean?
T of W1 is 0.
No, not here. No, this is image. This is image.
T of
Image means there exists some V1, which is
There
given
should be
in the
TV1 equal to W1, and that's
So there are pre-images of W1 and W2. Right? That then it will be inside the image, right? There is some V1 for which the image is W1. There is some V2 for which the image is W2. Right?
Yes, sir.
Is it clear to everyone?
yes.
Right. What about W1 plus W2? So my question is it belong to image or not? So is there any p-image of W1 and plus W2? It has, right? What is W1 plus
Yes.
W2? It is same as TV1 plus TV2.
V1 plus V.
And what does it mean? It is a linear transformation of V1 plus V2. So this V1 plus V2 is the p-image of W1 plus W2. Correct? So W1 plus W2 is in the image. Is it clear?
Yes.
Any doubt in this discussion?
No.
Okay. Great. Then tell me, suppose W is in the image. Is CW in the image?
Yes.
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 What is the image of that? Suppose
TV1.
W is in correct. So
Yes.
TV, there exists some V for which TV is W. Now what is CW? CW is C of TV.
CV.
So T of CV. So this is the P image, right? So CW is inside the P image. So image is a subspace. That is the point I was trying to make. This is a subspace. Okay. Now what we get from here? So let me draw the picture again.
Subspace of V or W, sir?
That is what I am going to ask. So this is V, this is W. Where image lies? Image lies inside W, right? Yeah. This is your image. right? This is the image space. This is the null space. This is going to 0. Correct? This is how the picture looks like. V to W, there is T. All the thing, take all everything in the domain. It is going to some here, something here, and this is the image. This is the image you have. Right? This is inside W. This is the image. W is the codomain. This whole thing is the codomain. This is V, the whole thing. This is domain of T. This is null space. Whatever is going to 0. So this is the full pictorial representation. Right? This is clear to everyone, this diagram?
Yes.
Yes. Now, when T is 1 to 1, I have said that this null space will be just 0. This is a singleton set. Only 0 will be there. Now, when T is on 2, what was the definition? This image and codomain should be equal, right?
Yes.
Image means range. Image means the one terminology you knew, that is range. Image and range are the same thing. Image set and range. So this range should be same as codomain, right? When T is on 2. T is on 2. The definition was the range T, or what I have written as image T, the same thing. This is same as codomain. That is, it should be equal to W. Correct? When this dotted area covers the whole W, then T is on. Correct? No doubt in this. Right? And here is the punchline. This range space, the image space, this is a subspace. I have proved that. Right? The dimension of this range space, this is called Rank-nullity. Okay? This is called rank-nullity. Rank of a linear transformation. Correct? Got it?
No, sir. This rank was I'm unable to relate it.
No, this is the definition. Dimension of the rank space is called rank of A. I mean, I am not explaining anything here. The definition of rank of a transformation is, it is the dimension of the range space. Understood?
Sir, is this range some opposite of kernel or something like that?
Range is the image space. The image, set of all images. This is the range space. This is the range space. Okay? Set of image, set of all the outputs. That is your range. Right? Are you there?
Sir, there I'm trying to understand.
So range is basically set of all your images, set of all output. That is a subspace of W, and that subspace is called range. Okay, range you have studied in maths 1, right? Range of a function.
Yes, sir.
What was that? That is set of all output, right? Same definition. Yeah.
Okay.
But here, one more property we have, that range is a subspace because it satisfies the property of subspace, as I have proved here, right? These properties. Correct? So range is a subspace. So subspace means it has a basis, so it has a dimension, right? And the dimension of the subspace, dimension of the range is called rank. That is the definition of rank of a linear transformation. Now, why it is called rank, I will come later.
Okay. Sir.
Okay? Is it clear? So, in this diagram, what we are seeing, the null space is subset of V, subspace of V, the domain. The range space is subspace of the codomain. This is on the other side. Null space is inside V, range space is inside W, when T is from V to W. Correct? The dimension of null space is called nullity. The dimension of range space is called rank. Is it clear?
Yes, sir.
Anyone has any doubt, you can ask me, because this is really a crucial topic. And somehow I got into the week 6 discussion. But that's fine. Anyway, we have to do it sometime. Okay? Is it clear? What? I have told till now.
Yeah.
Hmm? If you have any doubt, any question is coming to your mind, just ask me. No issue.
So nullity is uh, range of
Dimension of the space.
dimension of the null space.
Right.
Sir,
So dimension of the null space, let me write it here. This nullity. Okay. Got it?
Yes, sir.
Oh. So anyone has any doubt till this point? Please ask me.
So on two pins, that range should be equal to image.
Range should be equal to codomain.
Okay.
Right.
sir,
Codomain.
T has
Which
some
means the
matrix, right,
image.
sir?
Huh?
T has a matrix, right, sir? So rank of that matrix will be related to dimension of range,
That
sir.
is exactly same of rank of T. That is the point. Okay. So this is what I was about to write next. So let me again just briefly summarize what I have told you. R M to Rn, right? So TV is, I can write it like AV. Then where is your null space? Null space is inside this Rm, right? Null space is inside this Rm and range space is inside your Rn. Now null space of T is same as null space of A, right? That is what I have seen. So nullity will also be same, right? This is what I have written earlier. Now the new thing which I am adding right now, that is range of T or image of T. Same thing. What is that? Range of T or image of T?
Rank of
The dimension of it is basically rank of T. Right? This is what I am getting. And my point is this is same as rank of A. Rank of A. Okay? Right?
Sir, it's because one function, that's why we are able to write like dimension of range or either image vector space. It will be a rank, right?
What?
I'm saying like here, we're saying
No, here I am not talking about on two or anything. This is in general, whatever the function is. This is
why
always
we're
true.
talking about range of T or then image of T, either of these two.
The set of output. They are set of outputs.
Okay, yes,
Right?
yes, sir.
The point is, if T is on 2, now your question, if T is on 2, then what I am saying, range of T is same as codomain of T, right? That was the definition.
Yes, sir.
Basically, this is if and only if, right? Correct?
Yes, yes, sir.
Now, what is, so dimension of both sides should be same, dimension of the range and dimension of the codomain should be same,
Yes.
right? What is dimension of the range? This is rank, right? What is dimension of the codomain? So here codomain was
A.
Rn. This is the codomain.
N.
This is N. Okay? So this is the picture. So in general, if T is from V to W, not Rn to Rn, any V to W, if T is on 2, or if and only if I should write, T is on 2, if and only if rank of T is same as dimension of W. Clear?
Yes, sir.
If T is 1 to 1, what I have said earlier, nullity is 0. Got it? These two are the main result.
Sir,
Yeah.
in the first onto definition, we can get rank T equal to dimension only if nullity is 0, right?
Why?
Because then otherwise rank nullity theorem won't be satisfied.
I have not come to that position yet, right? No, why nullity should be, I mean,
Means then rank and nullity, if nullity is not zero, then rank and nullity would get more than n, and that is not allowed.
that is n, right? That is different. Here, what is the order of the matrix? What is the order of the matrix? Can you tell me?
Uh, n
Cross
cross
M.
m, I think.
n cross m.
N plus m,
N cross
right? So rank plus 90 should be equal to
m.
m, not n.
Okay.
Here it is n,
Okay, sir.
right? Because ranking is in this side,
Okay, sir.
correct?
Yes, sir. Yes.
Got it, no?
I was basically having the confusion of that RM, that how matrix is
Can
formed.
everyone just mute once? 1 minute. Yeah, tell me. What you are telling? Hello?
I think, sir, my doubt is clear.
Yeah, no? Okay, fine. So this is what I am getting. So this is the, I mean, main idea of this. And so in case of rank-nullity theorem, as you have already pointed out, so for matrix we knew this one, right? Rank A plus nullity A is same as, here it is Rn to Rm to Rn, right? Rm to Rn, so it was M. M there, right? So similar type of thing it is there. So M is dimension of which portion? Dimension of the domain, right? M was dimension of the domain. So similarly, if I want to write it, here I have this dimension of V. Okay, this is the rank-nullity theorem for transformation. The same thing we are doing, right? We are nothing special. I mean, this is the same thing, but instead of matrix, now we are talking about general linear transformation. Correct? Is it clear?
Yes, sir.
Now let's see what I was doing earlier. So I was defining a transformation from R3 to R2. How I defined this one.
X plus y, x minus y plus z.
Something like this, right?
Yes, sir. This only, sir.
Okay, let me check once because x plus y, x minus y. So this was I defined earlier. Okay, and what I calculated here, what was nullity? Nullity I have calculated, right? What was nullity?
1, sir.
1. Okay. So by using rank-nullity theorem, what I can tell about rank? Rank plus nullity should be what?
3.
3. Nullity was 1.
1,
So what was rank?
2,
2.
Now, if you remember, what was the matrix A?
2 cross 3.
Right? It is 2 cross 3. Right? And after the row reduction, at the final stage, what we got?
1, 0, half, 0, 1 minus half.
So what was the rank of this matrix?
2.
2.
2.
Number of non-zeros.
This is also here. Sorry, rank of A. Yeah, so this was 90 of A. This is what I was talking about. So now rank is 2 and nullity is 1. Now if I ask you, is T 1 to 1, you will say no, right? Because nullity should be 0. So it is no. Is T on 2?
Yes, sir. It's on.
It is on 2, yes. Because rank is same as
Equal to dimension.
dimension of
Dimension
the
of codomain.
codomain, right? The dimension of codomain here, codomain T is same as rank here. So it is same. Okay, so it is on. Clear? Understood how we can talk about all this?
Yes, sir.
Any doubt? Anyone has any doubt? Anyway, in which 6 we will again discuss all this, but still, is it more or less clear what I have discussed till now?
Yes, sir.
Yes,
So
sir.
you can see the relation between the matrix and linear transformation and all this, right? This is really important. This is the crack of week 5 and 6. Okay?
Clear, sir.
Okay, great. Okay,
In week
so
5,
let me.
excuse me, sir. In
Yeah,
week 5, there is a concept of change of basis.
that is what I have done, no? In the beginning of this here.
Oh, okay, sir. Okay, sir.
This is what I have written. Yeah. So more or less, this is. I mean, I have already covered week 5 and some portion of week 6 also. So I think all of you have pen and paper with you. Let's solve some problem to get an idea. You can see this presentation, right?
So which site?
Hmm?
Menti, we have to go to here.
So you can click and you can come to this page. So let's start with this problem. So I mean, I have taken some problems from activity question itself, but I want to discuss the concept basically. That was. So I have a matrix, linear set of linear equation. Then coefficient matrix, I am calling it as a what is the null space of it. So it should be easy to all of you. So first write down what is the coefficient matrix, and then try to find do the row operations and try to find out the basis of it. Not basis, but null space of it. Please let me know once you are done. So we will go to the next slide while we can give your answers. Got it? Should I go to the next slide?
Yes.
I am seeing 5 of you have more or less done it. So, let's see. You can put your options here.
Sir, can you show the option
You
one
want to put it?
second?
Yeah. x1 plus x2 plus x4, x2 plus x3, x1 minus x3 plus x4. Okay. So this is okay. Okay. So all of you are giving it number option 2. So how we are doing? Can someone just summarize it? What is the coefficient matrix?
1 1 0 1.
1
Let me write it on. 1
1 1 0 1 0 0 0 1 1 0 0 1 1 0 and 1 0 minus 1.
minus 1.
This was my coefficient matrix. So if I do row reduction, what should be my first step?
R3 minus R1.
Yeah, right. So 0 1 1 0. This is 0 minus 1. This is minus 1. And this is 0. Right? What should be my second step?
R3 plus R2.
3 plus R2. Correct. So if I do it,
1 0
so 0 1, I should have this one. 0 0 0 0. Right? And if I do this at the same step, R1 minus R2, then what I am getting? 0
1 0.
minus 1 1. Right? This is what I am getting. Correct? Is it correct what I have got here? Okay.
Yeah.
Sir, it is correct.
Okay. So how many
Two
dependent variables are there?
2.
Variables are there. Okay. So first one is x1 minus x3 plus x4 is 0. The second one is x2 plus x3 is 0. Right? So x3 and x4 are your free variables. Okay? So I can write x1 as x3 minus x4 and x2 as minus x3. So if I write this null space of A, what I should write? x3 minus x4 minus x3 x3 x4, right? Where x3 and x4 are in real. So if I write x3 as t1 and x4 as t2, so this is t1 minus t2 minus t1 t1 and t2, right? Where t1 t2 inside. Yeah. So can someone tell me what is nullity of t? What is nullity of t?
2.
2, sir. 2.
2. Why 1? 2 variables. 2. Right? If I want to write a basis, what it should be, what it should look like. 1 minus 1, 1 0, this is 1. And t2 is 1. So 1 0 0 1. This set will form a basis. Correct? So dimension is 2. Correct? And this is a dimension of this matrix is what? 3 cross 4, right? 3 cross 4. Correct?
Yes.
So what is the rank of this matrix?
2.
Correct? So in this case, you can see rank is 2. So rank plus nullity is same as 4. Rank of T is 2. Okay. So I hope all of you got this, right? Anyone has any doubt in this problem?
No, sir.
I am seeing at least 22 people are there, but only
Sir, please
30
show me the
people.
code, sir.
This is the code. No?
I missed that. That's why I didn't talk to the answer.
Okay.
Yes, sir.
Yeah. Okay. So if I go to the next question, this is one easy one. Find the nullity of the matrix. Yes. So first write the matrix. What this matrix is. 3 cross 3. And then
Sir, can you show the like solution for the previous one? Once for a minute.
this
So
one.
write it.
You don't have to write it. I will upload this. Okay. You understood how I am doing it, right?
Yes, sir. But
Then you don't have to write it down. I will upload this. You can see it from there.
okay, sir. But it
Okay.
like it helps to understand more like when we write.
Definitely. When I upload it, you will solve it again by yourself. Okay. So now I will prefer you to attend this next problem. That will be more helpful. Okay. Try to solve this one. Again a problem. Have all of you written the matrix at least? To begin with?
Yes, sir.
Oh, great.
Certain.
Yeah. Now do the row operation, and if you just find the rank, just do the row operation, find the number of constant rows, then you can directly find the nullity. You don't have to go to null space and everything. Because you know
Sir,
that.
in all the problems, basic thing we require is Gauss-Jordan elimination.
Exactly. Not Gauss Jordan, Gauss elimination.
Yeah.
Everything will boils down to that place. The solving system in AI. Okay. So I hope you have written down this problem at least. So you can type your answer. I think I can see your answer. What is this? I'm not sure about what this is. Some timer has started. I have no idea about this.
So the question was to find the rank or nullity, sir.
Nullity. Nullity.
Nullity.
That's our finding of nullity. Two, three. That's okay. Okay. So I think many of you have given this 0. Some of you have given 2 and some of you have given 3. So let me see what the answer is. So can someone tell me what is the matrix?
Yes, sir. 1, 1, 1.
So it is basically, if I write it in this format, this is how we generally write the elements of a matrix. And in each case, we have to take the minimum of this coefficient. I mean
1,
this
1, 1,
subscript. So it is 1, then
1, 1,
then
1,
1, 2, 2,
2. 1, 2, 3.
1, 2, 3.
right. So this is our matrix according to the definition. Now I have to find the nullity of this matrix. So again, do the row operation.
R2 minus R.
2 minus R1. what I
three
will
minus
get?
R.
3 minus R.
0, 1, and then R3
R3
minus
minus
R.
R.
So 0, 1, 2, right? Then what about the next one? R3 minus
R3
R2.
minus R2, sir.
Exactly. So 0, 1, 1, 0,
0, 0, 1.
1. Correct. And R1 minus R2. What I will get?
1 0 0 0 1 1
मुझे तो नहीं पता
0
होगा
0 1.
So if I do, I mean, you don't need that, but still, if you want to do.
1 0 0 0 1 0 0 0 1.
So identity matrix I am getting, right?
Yes, sir.
Now, what is the nullity? So, what is the rank of this matrix?
3,
3
3,
3. So, what is the nullity?
0.
0.
0.
Got it?
Sir,
Yes.
Yeah.
sir, is this portal working? Means it was showing 0 as wrong answer. I was just got
No, yeah, there may be some. Don't know what happened.
I just got confused, so that's why.
Yeah, I mean, something happened here. I also am not understanding what is happening.
Okay.
Okay, but 0 is the answer. Okay, you
So
got
rank is 3, no, sir.
rank is 3, right? Rank is 3.
Yeah, now we are left with 3 variables, no, sir. Then nullity should be
0.
What nullity should be? 0. Rank plus nullity should be 3, right? It is a 3 cross 3 matrix.
yes, yes, sir.
If you just
Okay.
calculate rank, then nullity is enough. And if you want to calculate null space, what is this? Null space of this matrix is which space? Can you
0
tell me?
space, sir.
What is null space of
0
this?
space.
0 vector space.
0 vector.
Because x1 is 0,
0 and
x2 is
x3 is
0, and
also
x3 is
0.
0. So only so it is only 0, 0. This vector. So dimension of it is 0.
Okay, sir.
Okay. Got it?
Yeah, yeah.
Yeah. Great. So this is also an easy problem. Let's try this. So this is something we need. We have discussed some portion of it in the earlier class. You written down this option in your paper. Just you have to check it as well. Should I go to the next slide? You can put your answer. So let's see what the answer is. What. Oh, fine. So, what about the first one? If nullity of a 3 cross 3 matrix is C, for any natural number between 0 and 3, that must be the case. Then what is the niety of minus A? The niety of a matrix A. There should be A. Then what is the niety of minus A? Can someone explain? What?
So it should be
Why?
same.
Yeah. Why?
Be the same.
Why?
Sir, it is just a negative of matrix and
Correct.
all the row operations.
Correct.
We would
So
just
if you
replace the
start with here,
symbols.
if we start with this matrix, if you put a minus here, so at every place it will be a minus, but it does not change the number of rows or number of non-zero rows, right? Only a negative will be there.
Only
So
sign
nothing will
changes.
change.
That's
Only
all.
sign changes. Correct? Is it clear to everyone that the first option is correct?
Yes.
Yes.
Yes, sir.
Anyone has any doubt in the first option?
No, sir.
No. Okay, great. What about the second one? Is it true?
No, sir.
No, sir.
Why? Why?
So
So
please
if it is
show.
not true, you should give me an example, right?
Yes, sir. If we
Yeah.
take
Yeah, go ahead.
yes, sir, I followed same with the matrix, sir. It is not true for matrix. That's why.
It is matrix. I mean,
Yes,
give
sir.
me an example.
Yes, sir. The same.
You take A is identity matrix and B is
Zero.
zero matrix.
Okay. Then it is same.
Then it is same.
Sir, if A and B both are the zero matrix, the
Sir,
A
when
plus
A is 1001, B is -100 -1.
So both the example are correct. Someone is saying about zero matrix, right? If you
Yes,
take
sir.
both as zero matrix, what happens? What is A plus B? This is zero.
It's also a zero matrix.
What is nullity of A plus B? That
2.
is nullity of zero matrix. What is that?
2.
So suppose it is n cross n. So what is nullity of zero matrix?
N.
N.
Right? The whole space. Right. And what is nullity of A and nullity of B?
N.
Both are n, right?
Yes, sir.
So n plus n. It is
It's
2n.
2n.
Right? So if n is, just greater than equal to 1, it is not never equal, right? So this is one example. Now another example, someone is saying that is if A is identity matrix, you take
B
minus
is
A.
minus I. Yes, sir.
B is minus I, just like the previous one.
Yes, sir.
Okay. So what is A plus B?
Zero matrix.
Zero matrix.
Null.
Right? So nullity of A plus B, what is that?
N.
N.
N. And both are n plus n. And nullity of A?
Yeah.
Zero.
0. Identity matrix. So rank is 1. Right? And nullity of B, that is minus
Zero.
identity, that is also 0.
0.
So this side is 0 and this side is 1. So it is not. Right?
Yes.
Understood?
Yes.
So both the example will work. Okay, fine. What about so idea of zero matrix?
Sir?
We have already understood. Yeah.
This can we write this plus as plus minus as well, because in minus also it would not be applicable.
In the first way of vector space, I have said plus or minus are not really different.
Yeah.
Minus is basically plus of.
Uh, and sir, another thing to ask, if instead of plus it would have been given like A multiplied by B, then how to check it?
Then you have to check it. There is some formula for rank of AB, right? For a matrix. But AB should be defined. Both A and B should be, A should be n cross n and it should be n cross r. This type of situation, right? AB is not always defined, correct?
Okay, sir.
Nullity of zero matrix, this is n, right? So option 4 is not correct, option 3 is correct. And what about the last option? Have you already encountered such situation? What about option 5?
Yes, we can take B equal to minus A.
So basically,
This I and minus I
I
example.
and minus I. This example will work there. option?
Yes, sir. We solved for the second option.
So A and B both are of nullity 0, but A plus B are of nullity n. So there exists of nullity. So option 5 is correct.
So 1, 2, and 5 were the answers, sir.
Fifth one is also correct.
1, 3, and 5.
1, 3, and 5. Okay.
Right. Is it clear to everyone that these three options are correct?
Yes.
Yes, sir.
Yeah.
Clear, sir.
Yeah. Great. Yeah. Someone of you gave option 4, but option 4 is not correct. Option 4 was this one, nullity of 0 vertex. Nullity of 0 vertex is n, the whole space, not 0. Rank is 0. Right? Okay, great. This one. So it has nullity has some relation with determinant.
Yes, sir.
So this is basically what. Let me see. What are the correct options?
Show the question, sir.
Yeah. Let me see. Answers. Okay. So what can someone tell me what is the relation between these two, nullity and determinant? Anyone?
Sir, if determinant is
RREF.
0, then nullity is non-zero, and vice
Why?
versa.
Why?
Why? Because nullity is defined only when one of the rows are 0, one or more. And
It is
since it,
defined anywhere. It is defined always. It is non-zero. What you are saying, right?
yes, sir, then determinant would be non-zero, right? If determinant is
I
non-zero,
mean, you are saying nullity is defined, but I am saying nullity is defined always. So you are want to say nullity is non-zero that you want to say, right?
yes, sir. Yes,
Sir,
sir.
when the determinant is non-zero, then the rank is n.
Correct. Correct. So basically, what is nullity? Nullity is, I mean, when nullity is non-zero, nullity of A is non-zero. That means this system of linear equation has infinitely many solutions, right?
Yes.
And nullity is zero means this is a unique solution
Unique solution.
because only zero is the solution in that case. So it is the case when it has unique solution. When it has a unique solution,
Zero solution.
Determinant non-zero.
That's zero solution. When it has zero solution,
When
when A is
determinant
invertible.
is
Determinant is
zero.
When A is invertible means A invertible.
determinant is
That means
equal.
determinant is
Non-zero.
clear. So if determinant is non-zero, then A is invertible, then it has a unique solution, then nullity must be
0.
0. When nullity is 0, then also determinant is must be non-zero.
No,
Clear? So you got which option are correct here? If determinant is non-zero, then nullity must be 0. It is correct, right?
Yes, sir. One is correct.
1 is correct.
Three is
Uh,
also.
so if determinant is non-zero, then nullity A may be non-zero. That is not correct, right? Because nullity must be 0. If nullity A is non-zero, then determinant A must be 0. It is also correct, right? Nullity A is non-zero, then determinant must be 0. So option 3 is correct, option 4 is not correct. Clear?
Okay.
So nullity A is non-zero means what? Nullity A is non-zero means it has infinitely many solutions. So it does not have a unique solution. That means A may not be invertible. A is not invertible. So determinant is 0.
0.
Correct? Determinant must be 0. So that is the option 3. Determinant must be 0. Clear? So option
Sir, 1
1
and 3 is correct. 3.
yeah, exactly. Option 1 and 3 are correct. Clear?
Yes.
Yes.
Okay, great. Yeah. Okay, this question. So
Sir,
this
show
I
the
think
previous question for the second.
previous question.
Yes, sir. Yes, sir.
Yeah. Okay.
Okay, sir. Thank you.
Oh, so one thing I forgot to mention that what is isomorphism? Isomorphism means when it is both 1, 1 and 1. When it is
It's
both
bijective.
bijective. So that definition I forgot to mention. Yeah. So this is what we have discussed today. About this. So this let me take a break for 1 minute. Yes. So let me see what are the options.
Sir, can you show the question
Yeah.
just one time?
Yeah.
Yes, done, sir.
Sir, please show the question slide once.
Okay, so what about the first option? Is it correct? T is 1 to 1 if and only there does not exist any non-zero vector v such that t v equal to 0. Is it correct or incorrect?
Yes, sir, it's correct.
Yes,
It's
correct.
correct because only 0 will go to 0. No non-zero vector will go to 0, right? So this is correct. What about the second option? T R2 to R2 is surjective linear transformation. Then it cannot be injective. So if it is surjective, the point is it cannot be injective. Is it correct or incorrect?
False.
No, sir.
False,
It's not
sir.
correct.
No.
This is
It
discussed
may
in
or may
tutorial,
not.
sir.
Can be.
It can
No, sir,
be or
it
it
must be, sir.
Always be.
So if you remember Rank-nullity theorem, so T is from R2 to R2. T is surjective. It is given, right? What does it mean? Rank T is what? Rank T is
2. 2.
2, right? It is subjective, same as dimension of R2. So rank is 2. Now rank-nullity theorem is saying what?
Nullity is 0.
Dimension of this R2, this domain, it is 2. Rank is 2. So what should be nullity?
0.
It should be 0. So what does it mean?
1 1.
1 1.
3 1 1.
T must be
1
1.
1.
Oh, it must be.
Must be. Okay, so if T is surjective and these two dimensions are same, so this is one application of Rank-nullity theorem. So these two dimensions are same, then T must be 1. Clear? This is what we have discussed today, right?
Yes.
Clear, no? Okay, great. Anyone has any doubt? You can ask me. Any doubt? I assume no, because no one has answered. So, what about the third option?
True, sir.
T is which is not injective, then T must be 0. You are saying it is true. Why?
No.
Sir, not injective means whole or R is in the null space, sir.
Why?
Not injective means nullity not 0.
Huh? Right?
And
Then why whole R is in the null space? You are correct, but why?
from rank nullity theorem,
Correct.
rank can be maximum 1. We are
Hmm.
saying nullity is not 0.
Hmm. Then you are actually saying it correct, but little bit finesse is needed. So T is from R to R. What is the dimension of this one?
1
1, sir.
1.
1.
What is the dimension of this one?
1.
1, right?
1.
Okay. So if I say rank-nullity theorem, then what should be equal to? It should be equal to dimension of this one, right? So 1. Now it is given that T is not injective. So nullity is non-zero, right?
So 1.
Nullity is non-zero. What is the maximum possible nullity?
1.
1.
1.
1. So nullity must be 1. Then nullity is 1 means rank is
0.
0.
Rank
0.
is 0.
And when rank is 0? When everything is going to 0. T is the 0 mapping, right? And nullity 1 means one dimensional vector space means this whole thing is going to 0. So T is basically 0 mapping. T of any V is going to 0. Right? Because both sides is of dimension 1. Correct? Is it clear?
Yes.
Clear, no? Rank T is 0 means what? Rank T is 0 means the dimension of the range space is 0. That means what? Range space is basically 0. Range of T
Range
is nothing
contains
but 0.
only 0
So
vectors.
everything is going to 0. The image is the 0 space. Right? So everything is going to 0 means what? Null space is the whole thing. And that really satisfies because nullity is 1. Null space is the whole thing. Null space is R. Correct?
Okay.
Got it?
Yeah.
Okay, great. Okay. What about option 4? If there exists some non-zero vector v such that v equal to 0 for a linear transformation, then t cannot be isomorphic. It's
So
true,
it is
right?
true from
Yes.
option
Not
3
1, 1.
only. You can conclude.
From 1 and 3 follows, sir.
Even anyway, not 1 and 3. I mean, uh, for non-zero vector v, t v is 0 means nullity is not 0, right? So t is not 1 to 1. So t cannot be isomorphic. Correct?
Yes, that's
So only from 1 it is followed.
Yes,
3.
sir.
Yeah. Okay, great. So this I think.
Sir, the previous option which you're explaining, can you just brief it once shortly?
So basically t is from R to R, where R are both R, domain and codomain, both are of dimension 1, right? Now from rank-nullity theorem, rank plus nullity should be equal to dimension of this domain, which is 1. Now t is not injective, that means nullity is non-zero, that we know. So nullity is non-zero, what is the maximum possible nullity? Because nullity plus rank is 1, so nullity can be maximum 1. So that is the case, nullity is 1. What nullity wants mean? Nullity 1 means this R is itself the nullity, because it is the dimension 1 vector space. And even if nullity is 1, then rank is 0, right? Rank of t is 0. What rank of t is 0 means? It means range is basically 0 subspace. So everything is going to 0. So whatever is coming from this R, everything is going to 0. So tv equal to 0 for all v belongs to R. Is it clear? So basically this is, here it is R, here it is R. Everything is going to 0. Yes. Yeah, this whole thing is null space.
So it's not injective.
And not injective is given. The question not injective was given,
Yes, yes.
which is not injective. Then what follows? tv equal to 0 for all. T must be 0, 0 transform. Okay, that's what we do. Clear?
So it's correct, or it's
You tell me, is it correct or not? What do you think?
when it's not injective, then
So you have not understood what I have explained, right?
yes.
Fine. Not injective means what? Not injective means nullity is non-zero, right?
Yes.
So what is the maximum possible nullity here? What are the
It's
options for nullity? Can you tell me?
like it can be 1 and even
Can it
0
be
is
more than
like
1?
rank. No.
Right. It can be 0 or 1, right? Nullity can be 0 or 1,
Yes.
correct?
Yes.
But T is not injective. That means nullity is non-zero. So what are the possible options for nullity? 1 only, right? Nullity must be 1. Correct?
Yes.
Your yes does not seem convincing. T is not injective means nullity non-zero. Is this question clear? I mean, I have explained this in my session, right?
Yes.
Are you there?
Yes.
I have explained this in this session. At least you remember that one.
Yeah.
Were you in my
I'm
session from the
getting
beginning or
confused,
no?
sir.
Just
I'm
now you
from the
joined?
beginning.
So I have explained this portion, right? T is not injective means nullity is non-zero. This portion I have explained earlier, right? I mean, now you should just go back and check again the recording. Okay. So I have explained this portion. If T is not injective, then nullity must be non-zero, because nullity is 0 implies T is injective, right? if and only. No? When T is injective, when T is injective,
1 to 1.
no, let him answer that. Where are you?
Okay.
Hello? Are you there?
Yes, sir.
When T is injective, do you know when a function is injective?
Yeah, when it's 1 1.
When a function is 1 to 1?
When there is a unique image, like when it's mapped uniquely to everyone.
So using that, in case of linear transformation, I have proved that the null space should be 0, right? Because no two element can go to 0.
Yes.
Correct? So null space should be 0 subspace. Correct?
Yes.
The null space should
Null
be 0
space should be
subspace.
0.
Correct? Now, what is the
Null space should be
dimension?
0 for 1 1. Okay. Yes.
Right, exactly. Now, what is the
Yeah,
dimension of 0
it's
subspace? What is the dimension of 0 subspace?
it will be 1.
Dimension of 0 subspace is 1, is it? Dimension of 0 subspace is 0. Right? Are you getting what I am saying? Dimension of 0 subspace is 0, right? No?
Yes, sir. I'll check it again, sir. I'm getting confused everything. Like I got it everything,
No,
but
when I
again
was
I'm
explaining,
missing.
then why did not you ask me that you have not
Yes,
understood?
sir.
When I was explaining, I was asking any doubt, any doubt. You have not told anything, right? Now it seems like you missed all the portion from
No,
there.
I was getting, but like I'm confusing everything now.
So basically, what I am saying, when T is, so now take this statement as true, okay? When T is injective, nullity must be 0, okay? This statement, take this as true statement, okay? Why it is true? I have mentioned that, you just go back and check. Now, when T is not injective, then nullity is non-zero, correct?
Yes.
Yeah. So here, what are the possible option for nullity?
Yeah, it's 0 and 1.
It must
Yeah.
be 1, right? Because either it is 0 or 1. Now it cannot be 0 as T is not injective. So nullity must be 1. Correct? So rank must be 0 because rank plus nullity is 1. Now nullity is 1 means rank must be 0. Correct?
Yes.
I mean, this is clear, no? 0, 1 plus 0 equal to 1.
Yes, sir.
Right? So rank must be 0. What rank 0 means?
Like range space will be 0.
Range space will be 0 because dimension of the 0 space is 0. So range is 0. Range is 0 means what? Every element is going to 0, right? Image is 0.
Yes.
Right? That is what I have said. So every element is going to 0. That was the statement. So this is a true statement. Clear?
Okay. Yeah.
Yeah, you just go back and think of this.
Yeah, I got it, sir.
Yeah.
Sir, are we done with the questions, sir?
Not really. I have, so this one I have explained, I think, right? Xy equal to x0. So is it 1 1 on 2 or which one? Can somebody just quickly tell it? We have discussed this. Is it 1 1 to 1?
No, sir.
I don't know why tomorrow no
Not
one
1 to 1.
is.
No, sir.
Because whole
Why?
y
One
axis
to one
is give
not
the
to
0 vector.
Yes, sir. Yes, sir. We
Yeah.
discussed this, sir.
Correct. So
It's
whole
not 1
y-axis
1.
is going to 0. Nullity is not 0. So it is not 1 1. Is it on to?
No.
No, sir.
No, sir.
Because What is the range
Because
space?
other than x0 means x axis, there is no point here.
Right. So range space is basically x0. So dimension of range space is 1. Rank is 1. But dimension of the codomain is 2. So rank is also not present. So it is neither 1 1 nor 1, right? So fourth option is correct. Clear? So we
Yes,
have
sir.
discussed
Yes.
this. Yeah. Great. So fourth option is correct in this case. Okay. Yeah. Great. Uh, so this one I think is in your activity question. So have anyone of you done this? So I think there are two more questions left. This one and this one. So these two questions I will do. So this is basically a simple checking. Everything is from V to V, and the composition function you know that this is how it is defined. T composes. First you apply S, then you apply T on that. This is how it is defined. So it has nothing to do with transformation basically. It is what you know for function, that is enough. So if the composition is injective, then which one, T or S, which one is injective? That is the question. So if I take the first one, so injectivity, TSV. So my claim is S is injective. Suppose SV1 equal to SV2. If this happens, if I apply T, so I am assuming T compose S is injective. First I am assuming this. I want to show S is injective. This is what I want to show. So how we will do that? So I take T on both sides. I apply T on both sides. Now this T composes, so this is T composes V1, this is T composes V2. Now this is injective. What does it mean? V1 equal to V2. So I started with SV1 equal to SV2. I have proved V1 equal to V2. What does it mean? Is it clear?
T must-
Sir, will it be same for T as well?
No, it cannot be, right? Because T is coming after S. So if I start with T V1 equal to T V2, then I cannot apply S, because when I apply S, it does not matter because T compose S is injective. We don't know what S compose T is.
Oh yes, T is appearing before S. Order is important.
If we know S compose T is also injective, then we can conclude that T is also injective, right? So this is the catch. So it may not be, for T may not be injective, but S must be injective. Correct? Now what about the surjectivity? T compose S is surjective, that we know. This is given. So my claim is T is surjective. How we can show it? T is from V to V, S is also from V to V. So this is surjective, I know. So I take an element from here, V. Any element from V. I'm taking an element from here. T compose S is surjective. What does it mean? There exists some V prime inside V such that it has a P image, V has a P image. Right? Because T compose S is also from V to V. So I'm taking V from here. V is here. So T compose S, V prime is V. Is it clear to everyone? At least this step.
No, sir. Please explain us again.
So T compose S is from V to V, right? Because T and
Yes,
S
sir.
both are from V to V. So if I compose this two, this is from V to V. Now, my claim is T will be surjective. So what I have to do? I have to take one element from V. I have taken V from V. Now this element is also in this V. This V is all same. Now T compose S is surjective. What does it mean? There exists some element here as an input which is going to this V. So let this element be V prime. So there exists some V prime in V such that T compose S, V prime is
Yes,
V.
sir.
Now what does it imply? T of S V prime is V. So S V prime, this is my pre-image of V with respect to T. So if I call this S V prime as my V double prime, so T of V double prime is my V. So V has a P image. I have chosen V from here, I have a B image here. Correct? So T is surjective. Is it clear? So this is basically function. There is nothing to do with the solution. This is just property of function. Clear? Is it clear to everyone?
Yes.
Yes.
Any doubt? Okay. So which options are correct? So first one is correct. D. So second one is correct.
Second, third,
And
sir.
2 and
Second.
3.
second,
Yeah.
2 and 3. Correct. Okay. So the last question. This one you need to solve. So this type of problem I have solved, but let's see this example you can do it. So basically you have to check what is rank and what is nullity. That is it. Even if you just know nullity or rank anything, you can just not do. Please let me know once you are done. Okay, any one of you have done this? Yeah, so one.
Sir, please show the options.
How can both 2 and 3 be correct? Whoever have given the option, he has given both the correct option, but how can both 2 and 3 be correct? This is T is 1 to 1, but not on to. This is T is on to, but not 1 to 1. Both cannot be correct, right?
Sir, please
Yeah.
show that option slide.
Only 5 of you have done. Okay, so let me write it somewhere. Can someone tell me what was T? You have written also. What was T?
2x plus 3y, 5x minus y, x plus 6y.
Correct. So first I want to find the nullity or whatever. So if I write this as my matrix 2, 3, then 5 minus 1, 1, 1. So this is the matrix.
Sir, 1 6.
1, 6, sorry. So this is my matrix more or less. So if I want to find the null space of T,
Sir, if it's R2 to R3, then don't we write to Z component also in the matrix?
This is the Z components, no?
0 uh, in the matrix formation.
No, I mean this is where this is coming from. This is coming from R2. A into V, where V is coming
Okay,
from.
sir.
If V equal to AV, this V is coming from the domain, right? So this is coming from R2, not R3. The image in inside R3. So whatever I get, this is a 3x1 matrix. That is this one. Correct?
Yes, sir.
Got it?
Yes, sir.
Yeah. Yeah. So if I want to find the null space, what I have to do basically, I have to find all those xy such that txy is going to 0, 0, 0. So basically, I have to solve this equation. 2x plus 3y is 0, 5x minus y is 0, x plus 6y is 0. Which xy will satisfy this? This is what I need to find from the null space. So basically, I have to find the null space of this matrix because the coefficient matrix is the same. And that is what I have explained. So if I do this, what I should get? What is the first step?
R1 by 2.
And then what is the second step? 5 minus 1, this is 1, 6. What I should do
R2
next?
minus 5 R1.
R2 minus 5 R1.
R3 minus
What I
R1.
get? R3 minus R1. What I get?
0 minus 5 by 2.
Minus 15 by 2. Right?
Yes, sir.
And this is 0 and 6 minus 3 by 2. So basically what I am getting, so this matrix is nothing but 1, 3 by 2, 0. This is
minus
We
17.
divide with that, no, sir. 0, 1 it becomes.
huh?
I mean, in the next step, we can go for R2 by minus 17 by 2.
So this will become 1. So
Yes.
basically this I can make it 0. This will
0.
become 1.
Yes, sir.
This will become 0. So after some operation I will get 0,
1, 3.
0, 1. This one. Right?
Yes, sir.
So what is the dimension of null space? What is nullity? What is nullity?
0, I guess.
0, sir.
Why you guess?
1.
It is
It is 0, sir.
So null space, if we calculate it, so basically, if I do x equal to 0 and y equal to
Y
0,
is 0.
so null space is nothing but the 0 subspace.
So nullity is 0.
So nullity is 0. So D is
1, 1. 1 to 1.
D is 1 to 1. Now this is done. Now what about rank?
Rank is 2.
Nullity is 0.
2.
Rank is 2. Now can this D be on 2?
Yes, sir. It is dimension.
So it is not on 2, right?
Oh,
Dimension
sorry.
is
Not on 2. Yeah, yeah.
not on 2. Yes. Because dimension of the codomain is
3.
Not equal to rank.
not equal. Here, so T is 1 to 1, but not 1. So which option is correct? T is 1 to 1, but not. Second option is correct. Okay. I don't know why many of you have given thought.
So please go to the solution page once.
Yeah.
Go down the page. Okay. I mistaken the line solution. Okay. One second.
Okay. So you understood this problem, how to do this. So this type of problem now I think you can solve it, right?
Yes, sir.
Whatever this type of problem is, just get here. Yeah. So that is all I had to say for 5. 5 is end. So in the next session, maybe some topic of week 5 will be discussed. So go back and see what we have discussed in this yesterday and today. See what we can get from here. Hope something is it is helpful.
Thank you, sir.
Yeah.
Thank you.
I hope the discussion helps somehow.
Yes, sir,
Right?
definitely, sir. Now we have to go for the practice assignment, sir.
Yeah.
Today is the deadline, and definitely it helps a lot.
Thank you,
Your
sir.
practitioner
Thank you,
deadline
sir.
is shifted to tomorrow.
Yes, sir.
Practice assignment, sir.
Tomorrow it is shifted tomorrow.
Okay, thank you, sir. Yes,
Thank
sir.
you.
Right, sir. Thank you, sir.